All right, so one of the other things that you need to take a look at in Chapter 12, along with these intermolecular forces, has to do with the solubility of different substances within one another. And this is addressed early on in Chapter 13, but you also need to understand a little bit of it right now because it's really strongly related to these intermolecular forces. And the end of this chapter asks you to do several problems related to this. So this is taking a look at solubility. And it's quite a bit different than what we were doing earlier in the semester when we were looking at that solubility table on the cover sheet of your exams, or that table that I gave you to do a lot of these problems with. We're not talking about taking an ionic solid compound and trying to dissolve it in water. What we're talking about now is taking two substances, maybe two liquids, and seeing if I can dissolve one in the other. So I'll give you a brief description right now, and then you'll see more on this early in Chapter 13. So you'll see this same phrase again. Like dissolves like. And all that means is that if I have two substances that have similar types of intermolecular forces, they will dissolve in one another. Their attractive forces will cause them to mix together and dissolve. So let's say that I've got a beaker. And let's say that I've got some substance, and we'll call these little circles, we'll call those water molecules. And these little squigglies, again, are my intermolecular attractions between those water molecules. And let's say that I try pouring some oil in here. Just from your common experience, predict what you think is going to happen. Have you ever seen oil mixed together with water? If you make salad dressing, you put oil and water together and you shake it up and you get these little globs of oil all over the place, but they never dissolve into the water. Or if you go outside and you see a puddle with some oil sitting on top of it, you see that there's just this shiny kind of iridescent layer of oil floating on the top of the water, but they just don't mix together. So we'll use these ovals as representing oil, and I'm going to call these hydrocarbons. And we'll use something like CH3, CH2, CH3, which isn't technically oil, but it's a hydrocarbon compound, and it's easy and small for us to draw on the board. But basically, oils are carbon and hydrogen containing compounds, just really large molecules. So we're going to use that oval, and let's say we pour some of that in here. And I think you should know from common experience that they don't mix together. But if you don't know from common experience, then you're just going to have to trust me or try it later today. So all of these oil molecules also have attractions between one another that keep them in this liquid form. Now, in order for me to get these two layers to mix, what I really have to do is I have to break the attractions between each of these sets of particles and get them to interact with each other and form new attractions between dislike particles. So what kind of intermolecular force is the strongest type present in the oil, or in this CH3, CH2, CH3 molecule that I've drawn out? Well, remember, carbon-hydrogen compounds are always nonpolar. So as soon as you look at that, you know it's nonpolar. You know the strongest type of intermolecular force there is dispersion forces. And then I've got water here, and we know that that has hydrogen bonding, which is a much stronger type of intermolecular attraction. So essentially, what I'm going to do is I'm just going to take a little square here and I'm going to blow it up. So here's my oil particles and my water particles. And there's some sort of interaction here. So in order to get the oil molecules to dissolve in the water, I have to break this attraction. And remember, it costs me energy to break those attractions. You know, I have to pull those molecules apart from each other. And I have to pull these two apart, and I have to break this. And then what I essentially have to do is somehow get this molecule to insert itself and form new attractions to the neighboring molecules of the other type. Now, if these don't have similar types of intermolecular forces between the two substances, these newly formed attractions aren't going to be strong enough to give me back all the energy it costs me to break apart the others in order to make this happen. So that's why we use the phrase like dissolves like. These are two very dissimilar types of substances, and so they are not going to dissolve in one another. But what could I get to dissolve in water? If I had something like methanol, this is another compound that has hydrogen bonding present. So I would predict that the methanol in the water should dissolve in one another. Or ethanol in water, which is just regular liquor and water, and you know that those things mix together. Methanol is just a wood alcohol, and you know you can get that to mix together. So let's do one sample. Let's try something that you might see on an exam or a homework question and use this information. And again, this is described in a whole lot more detail in Chapter 13. So here's an old exam question. In which of the following will methane, or CH4, dissolve? And remember, dissolve just means that it's soluble. And let's list those. We've got C6H6, NF3, CH3OH, and water. So again, we want to take a look at this compound up here that we want to dissolve in another substance, and we have to ask ourselves, what's the strongest type of intermolecular force that is present here? So it's nonpolar, and why do I know that without drawing it? Because it only has carbon and hydrogen, and that means the strongest type of intermolecular forces there are the dispersion forces. So if I want this stuff to dissolve in one of these things on the list, I have to find the substance over there that is most like this compound and only has dispersion forces. So it has to have the same type of intermolecular force. So if I go down the list, well, the first thing that I find is a carbon-hydrogen compound. So I know that this is nonpolar, only has dispersion forces. And I could probably stop there, but let's go through and double-check everything else. So this NF3, I know that it's polar. If you don't know it's polar, then you want to draw out the Lewis structure and make sure you're counting valence electrons and not just drawing dots. I am actually counting them in my head. So here's the compound. It's a polar compound. So it's polar. It means it has dipole-dipole forces. I get to the methanol, and I see that oxygen bonded to hydrogen, so I know, again, that it has hydrogen bonding. And I get to water, and I know that that has the OH bond, and that fits into the hydrogen bonding category. So it looks like we have to go with the C6H6. So methane should dissolve in hexane, which is what this represents, or actually benzene. So we've got dispersion forces. Dispersion forces, similar intermolecular forces, will dissolve in one another. So give some of those a try. You'll see different sort of flavors of the same type of question, but they're all based, again, on the same types of intermolecular forces causing two substances to be soluble in one another.